Welcome to the first video of section 3.3 on partial derivatives. The goal of this section is to calculate and interpret the partial derivatives and higher order partial derivatives of a function of several variables. Before we do that, let's review a little bit what things looked like for a function of one variable. For a function of a single variable, the derivative at a point x equals a gives the instantaneous rate of change. So the instantaneous rate of change of the function at a. If we wish to examine the instantaneous rate of change of a function of two variables, well then we're looking at a point AB, and we end up by encountering the same issue that we did with limits, namely the instantaneous rate of change in which direction. There are infinitely many to choose from. Let's just take a quick second and visualize this. If we have a function of a single variable, then when we're talking about the instantaneous rate of change, there is one natural direction. So if we're at a point A, then the instantaneous rate of change is in the direction of the positive increasing input variable. There's only one, and so we end up by having the instantaneous rate of change being the slope of the single tangent line. But if we're in a function of two variables, then we're looking at a domain point AB, and if we draw a function surface above that, the rate of change of the function, so if we have our image point up here, well, the rate of change if we go down in this direction is not going to be the same as if we go over in this direction, as if we go up in this direction. So how do we decide what we mean by rate of change? And so what we're going to do, first of all, is privilege two out of the infinitely many directions, and those are the directions of the coordinate axes. So the direction in the positive x and the positive y axes. First order partial derivatives. They're called partial because they are partial. They're two out of infinitely many directions. So if we remember again from the first calculus course, the derivative f of a function of one variable at a point x equals a is defined as a limit. So f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h. And graphically, what that represented, if you had a point a and f of a, so this is the graph of f of x, and you have some distance h, so we move over to a point a plus h on the graph, so a plus h and f of a plus h, then the line drawn between those is called the secant line. And that secant line, that slope, is delta y over delta x, which ends up by being f of a plus h minus f of a over h. And if we take the limit as h goes to 0, then we end up by getting the slope of the tangent line. So the slope here is this limit f prime of a if that limit exists. And so that is the inspiration for the following definition. Definition 3.3.1, let f of xy be a function. The partial derivative of f with respect to x at a point AB is, now this notation is something new, we'll talk about that in just a second, del f, del x, evaluated at, that vertical bar we've seen before, again means evaluated at, AB is also a limit. It's a limit as h goes to 0 of f of a plus h, b, minus f of ab over h. And you'll notice that the h appears only in the x component, a plus h and f of a. The b remains constant or fixed. So just a little bit of notation here, the symbol, this curly D, is pronounced del. So del f, del x, this symbol is, well, del f, del x, or, said longhand, the partial of f with respect to x. And the reason we use this curly symbol is to distinguish it from the derivative of a function of a single variable where you use d, df dx. Talking about notation, there are many, many different notations for partial derivatives. So if we had z as a function of f of x, y, all of the following, all of these are equivalent notations for the partial derivative of f with respect to x at ab. F sub x of ab, f sub 1 of ab, z sub x, d, capital D for derivative with the x, d sub x of f of ab, d sub 1, del z del x evaluated at ab. All of these are the same thing as del f del x evaluated at ab. And the x, well, the x subscripts are pretty obvious. We're taking the derivative in the x direction. The 1 subscripts are because x is the first variable. So there's the interpretation. That's what the, not the interpretation, there's the definition. That's what the limit is defined as. What is the interpretation of this? So let's draw the equivalent picture to what we had in a single variable. So we're looking down at a point AB. As always, that's really the point AB0, but we're imagining it in the input space, AB, as in R2 in the variables x and y only. We have a surface, a function graph floating somewhere above this point. Get that a little bit of shading. And this function passes the vertical line test, as all function graphs do. And so this point AB is somewhere up here on the function surface. That's AB and f of AB. In the definition of the partial derivative, b was kept fixed. B did not change. A and a plus h, we were making little changes to a, but not to b. So if we keep y fixed at y equals b, we actually end up with an entire plane. This plane here, that's the plane where y is equal to b. And if we look at the intersection of this plane with our function surface, two surfaces intersect at a curve. So we have a curve of intersection of the plane y equals b, give that a little bit of shading, and the function surface. So this partial derivative, this is the rate of change in the x direction, meaning it is the instantaneous rate of change going in that curve. If we go from AB in the positive x direction, then we're looking at the instantaneous rate of change, which can also be thought of as the slope of that tangent line which is parallel. That line is parallel to the x-axis. And the slope of that line is exactly the partial derivative f sub x evaluated at AB, which, remember, is another notation for del f del x evaluated at AB. So our takeaway number 7 is exactly this. F sub x of AB is the instantaneous rate of change of the function f at the point AB in the direction of the positive x-axis. Geometrically, it is the slope of the tangent line to the curve of intersection of the plane y equals b and the function surface. Exactly here, the curve of intersection of the plane y equals b with a function surface, and the partial derivative with respect to x is the slope of that tangent line. It's the instantaneous rate of change of the function in the positive x direction. So we can do an equivalent definition for the partial with respect to y. So let's do that. We'll go through it a little bit quicker now since we have the basics down from our derivative with respect to x. So definition 3.3.2, let f of xy be a function. The partial derivative of f with respect to y now at a point AB is del f del y evaluated at AB is the limit as h goes to 0, and this time we're going to incrementally change the y component. So f of a b plus h minus f of ab over h. Similar notations, if z is equal to f of xy, then the equivalent notations are f sub y of ab, f sub 2, because y is the second variable, z sub y, d sub 2, del z del y evaluated ab, and del f del y. Interpretation, well, we have an analogous graph that we can draw. So let's go back and put our point AB down in the xy plane. Let's put our function graph above it. Now, in the definition of the partial with respect to y, it's x that's being held constant. Right? X in the definition doesn't change. X is equal to a in both cases, which means that graphically that's like holding x in a plane. And that plane, of course, is going to be the plane x equals a. And that plane intersects the function surface just the way the plane y equals b did previously. And so we have our image point up here. Give a little bit of shading again to our point, to our plane x equals a. And so the analogous situation here, if we're looking at the partial with respect to y, then we're looking at the instantaneous rate of change of the function in the positive y direction. So we're looking at the instantaneous rate of change along that curve in the positive y direction, which can also be interpreted as the slope of that tangent line. So the slope of this tangent line is exactly the partial with respect to y, f sub y, evaluated at AB. So takeaway 8 is exactly that. F sub y of AB is the instantaneous rate of change of the function f at the point AB in the direction of the positive y-axis. Geometrically, it is the slope of the tangent line to the curve of intersection of the plane x equals a and the function surface. One last definition for this video, and that is the partial derivative functions. So the previous definitions were at a single point, AB. Now we're talking about creating a partial derivative function for any point xy. The definitions are completely analogous. So for a function of two variables, del f del x, which is f sub y of xy, is the limit as h goes to 0 of f of x plus h, comma y, minus f of xy over h. Again, we're taking the derivative with respect to x, so it's the x which is being incremented. Del f del y, the partial derivative with respect to y, or f sub y, another notation of xy, is the limit as h goes to 0 of f of x y plus h, this time minus f of xy over h. And in general, if we have a function of n variables, then the partial derivative of that function with respect to the ith variable is del f del xi, or f sub xi, there's a little I missing there, f sub xi of x1 through xn is the limit as h goes to 0. It is the ith variable which is incremented. All the other variables are being held constant, minus f of x1 through xn divided by h. So that is the definition of these instantaneous rate of change of these partial derivatives. Those are the geometric interpretations. In the next video, we will see how to calculate them.